you've heard a lot about deep learning over the course of the last few days and probably the entire week. And we have models that can recognize things in images, generate text in images. The models can learn to play a number of two-player games and also predict the structure of folded proteins. So, as hopefully you've gathered through the last day and a half, we don't understand what's happening in deep learning all that much. And what I mean by understanding here is, understanding is sort of a vague thing, but what we mean here is that in deep learning, what do? We make a lot of, we train models, right? But we make a lot of choices about the initialization, the architecture, the optimizer, regularizers, and the data set. That's a whole other can of worms. We make a lot of choices and we get models. And my vision or version of understanding would be how do the choices we make over here affect the model that we get? And are there better or worse choices that we can make for these to get to affect how models perform and behave in different situations? So so far, key theoretical questions in deep learning you can sort of slot under three different buckets. There's architectures or representations. Tommy's talk on yesterday morning talked about what kinds of functions can you express with deep architectures. What kind of architectures are efficient in the number of parameters that you have, and so on. And under this, I'd also like to put in what kind of representations can we learn using neural networks. There's a whole bunch of questions about optimization, which are, so basically to train a neural network, you gather some data, or maybe you, this is probably more for a fixed data set scenario where you have you have a data set and you want to fit your model to that data set, and how do we reach the global minimizers of the empirical loss. And in this talk, I'll be exploring a bit about characterizing these global minimizers. And you have generalization questions, which are, does the solution that you get through optimization actually perform well on the population, or in new scenarios when you only have access to a finite number of samples? So the first part of the talk will be about the optimization, and then I'll touch a little bit about generalization towards the end. So yeah, let's try to look into what neural collapse is. So in the modern practice of deep learning, when you have a finite data set again, a typical approach is add more layers, take a bigger network, make your network as big as possible to fit the data set, and that's usually a good strategy for generalization. So we use deep networks that are over-parameterized. They're usually trained to fit the training set. So yeah, you try to hit zero error in terms of accuracy. And then often you try to go beyond that to try to really hit zero training loss, or hit global minimizers of the loss function, the empirical loss function. And this is the terminal phase of training. And what happens at the end of this, some experiments, some empirical measurements from a couple of years ago at this point characterize this phenomenon called neural collapse. So what is neural collapse? So before that, we're going to look at deep networks, and we're going to conceptually split them into the map all the way until the last layer, and then just look at the last layer. So the map all the way into the last layer we're going to call H, And then you have the classifier layer, which is we're going to call WL. WL because you have L layers in the network. And this is the balanced data set is going to be from a classification problem. And so you have C classes, and you have n samples per class, and you have the same number of examples per class, and you're trying to you're trying to minimize the loss function on this data set. And let me also define a couple of statistics for you. So you have the class means, so for each class, you take the feature vector at the last layer, and you can calculate the mean feature vector for all of these, and you also have the global mean. And so those are the so in this ball and stick model here, the blue ball and stick are the mean vectors. The yellow, the blue balls that are floating around here, those are the individual feature vectors for different samples. And the red ball and stick corresponds to the classifier, and the classifier vector, and you have as many classifier vectors as you have classes, right? Because at the last layer, you're mapping your feature vector from one from whatever dimensional representation to a score for each class. So you have as many classifier vectors as each class, and we can define the within class covariance, which is how much these the small blue balls are spread around their mean, or spread around the big blue ball and stick. And you also have the between class covariance, which measures the between class covariance, which measures how far these classifier vectors are from each other. Okay. And finally, so in this figure, you might have noticed these green dots. Those are those make up something called a simplex ETF, which is basically a collection of vectors. And it's an equiangular tight frame is a set of vectors in a space which are all the same angle from each other. And this is an interesting object because an equiangular tight frame is also the solution to if I have a bunch of vectors and I want to put them as far away from each other as possible, an equiangular tight frame is the solution to that problem. Here we're going to look at something called a simplex equiangular tight frame, which is apart from having the vectors having equal angles from each other, they also need to lie on a plane. And you can show that the canonical simplex ETF is basically looks like this. You can write it down in closed form. And this, if you think about it for a second, is just the, this is an operator that takes a bunch of data and computes the mean of that data. So this is this is the canonical simplex ETF. So having defined, yeah.
This is a matrix, right?
Yeah, this is a matrix.
So what the matrix defines?
I'll tell you what the matrix defines once we get into the definitions of neural collapse. So just keep this in mind. So I've given you a bunch of statistics. What is neural collapse? It's basically this GIF over here. Okay. So this GIF is an evolution of what happens to the feature vectors, the classifier vectors over time as you train them, and you'll see that all of the so you'll see a couple of things happening. All of the little blue balls are converging to the big blue ball and stick. The classifier vectors, which is the red ball and stick, those are converging to the blue ball and stick, and both of those both of those objects are also converging to the green balls over there. So you can define this in empirical measurements. So the first condition is variability collapse, which is all of the little blue balls are converging, the individual feature vectors are converging to their mean. So if you measure the within class covariance normalized by the between class covariance, you see that it goes down over time. These conditions are called NC1 through 4. NC2 is the condition that your mean vectors spread out to be as far away from each other as possible, which is captured by this simplex ETF. So all of the mean vectors have the same norm, and they have the same angles with each other. And then the third condition is feature weight duality, which is the classifier vectors and the mean feature vectors. Those are duals of each other. So if you measure those, if you measure the distance in Frobenius norm, you could do it in other ways too. You'll see that those start converging. And finally, this allows you to describe the deep networks. The function that the deep network implements is check, instead of passing it through the weight matrix of the last layer, check which mean feature vector you're closest to, and assign that as the class label. And you'll see that if you use that rule, the disagreement with the deep networks rule is basically 0. So this is how the deep network is solving the problem. Okay. Yeah.
Sorry, could you just say again the bottom left one? What's the difference between?
The classifier vector and the classifier matrix, the last layer weights, and this is you construct a matrix with the mean feature vectors, not exactly the mean feature vectors, but the mean feature vectors centered around the global mean. And if you look at the distance between these two matrices, that goes down to 0. Great. Yeah. And of course, please keep the questions coming. I'm happy to stop. I don't have to. I don't have that much to go through. Yeah.
Sorry, again, just a clarifying question. So, what you said at the very end, essentially the model doesn't complete passing an input through all of the layers, but rather just goes to the closest vector to the mean vector?
No, I'm saying you compute so you pass your input through all of the layers, and you get a feature vector at the end, right? So what the deep network would do is then pass it through the classifier matrix, and then you pick the maximum one. I'm saying instead of that rule, map the feature vector to the class mean which is closest to it. And those two rules are doing the same thing. Okay? So just to write these down mathematically, so we have a formula for them. Variability collapse, all of the, in the extreme case, like all of the feature vectors are exactly equal to the mean. The equinorm and equiangularity of the central class means. And so that basically says that the central class means form a simplex ETF. Then you have the self-duality of the classifier matrix and the last layer features. Again, collect your centered class means into this matrix, and these are the if you normalize them, they're the same matrix. And finally, you can do the nearest class center classification rule, and that does the same thing as the classifier. So, yeah, what are some implications? So we have a nice geometric characterization of deep networks at the last layer. So I know this is this was essentially just like a linear model, right? So maybe that wasn't not that it's not surprising, but that it's intuitive. One implication of this is that you don't actually need to train the last layer. Just set it to be a simplex ETF, and you'll get a model that performs just as well. And in fact, this was true of earlier models. Not sure exactly how it works, how it maps out now, but a lot of the weights were in the fully connected layer. So you can save a lot by just setting that to be a simplex ETF. Then Tomer's done some work on using the implications of neural collapse for transfer learning, and basically you can, if you understand what the representations look like at the last layer, hopefully you can also trace that back down to understand which representations are good, and hopefully I'll get to this a little bit later in the talk. It might help us understand how generalization happens in deep learning. All right, so first part of this, so all of this that I described so far, this was from this paper in PNAS from 2020. I'll get to what we did. So first, can we actually prove that neural collapse emerges? Is this so? This seems like a intuitive thing. Is this something that happens in specific situations, or can we show that this is the natural solution that you should expect out of training a deep network? So you can show that with a nice mathematical model. So here we studied deep homogeneous relative networks. So you just remove all the biases. Not saying the biases are pretty important, but just for this case, let's focus on this type of network. And if you and we're not going to look at this network on its own. Instead, since we're working with ReLU activations, what we can do is normalize all of these matrices and pull out a single parameter, a single scale parameter rho. And this is specifically, this is the same rho that Tommy used in his talk yesterday, and that is the product of the Frobenius norms of the matrices. And you can write down the regularized empirical loss on a balanced data set as basically squared loss plus a weight decay term. So given this model, we can, before we show that neural collapse exactly emerges, we need one piece of we need one result, a lemma called that tells you that the output of a network, when you've optimized it to hit global minima, the outputs need to correlate with the labels. And so first, what we do is the labels are not the one-hot vectors, but since we're using homogeneous networks without biases, which can represent zero mean functions, let's also center and scale the labels so that they look like this. And then when training a deep network using this regularized square loss, the lemma that we're going to try to derive is when we train a deep network using the regularized square loss, we don't fit the labels exactly, but even if you don't fit them exactly, the outputs are still aligned along the same direction as the label, as the centered labels that you're looking at. So we can show that these solutions are global minimum of the regularized square loss. It's fairly easy, so I'll just go through a few steps. You rewrite the loss in terms of a couple of different statistics. This is sort of like the second order moment of the outputs, and this is this captures the correlation of your outputs with the labels, and minimizing the loss with respect to just the scale parameter rho. You get a solution for rho, and then plug that back in, and you'll get this. And I'm not going to show that exactly, but the loss is minimized when this quantity mu is maximized. So the outputs are correlated with the labels of the network, labels of the data set. Okay? And since this is a classification problem, you'll also, you might wonder, do all of the outputs exactly map to the same value when I actually train my network? And the answer is yes. If you do that long enough, you'll see at the beginning of training, if you track the correlation that is spread out at the first in the early epochs, and then as you go down, the correlation concentrates over training. Okay, so using that, using the lemma of the outputs are correlated with the labels, you can show the emergence of neural collapse. So if you train a ReLU homogeneous deep network on a balanced data set with with regularization and using the normalized network, then the points of convergence satisfy the conditions of neural collapse. Once again, I'll do a quick sketch of this. So essentially, how we can show this is if you just look at the gradients and you realize that these are correlated with the labels, then by working through some algebra, you can show the four conditions. So for the first condition, actually, you need to consider two different batches of stochastic gradient descent. So you have too many batches which are exactly the same except for one sample, and you can show that since we're assuming you've hit full convergence, both of these gradients need to be equal to each other and equal to 0, and that's how you can show that these features are equal to each other. You can show the duality between the features and the classifier weights by again considering the entire the full batch gradient, since that also needs to be 0 at perfect convergence, and you can get that these are proportional to the centered class means. And finally, again, I'm not doing the calculations. It's fairly it's tedious but not hard to show that you can get the closed form solution for the classifier weights, and you can compute their angles, and you see that they're all the same norm and they have the same angle with each other. So you can show that NC2 is satisfied as well. Okay. Yeah.
This is under the assumption that the data set is balanced, right?
Yeah, the data set is balanced, yeah.
And if it's unbalanced, do you know what happens?
If it's unbalanced, there's a nice paper from 2021 called, which looks at this in extreme imbalance. It's called minority collapse. And if you have one class with much smaller amounts of data than the others, you'll see that classifier vector essentially collapses onto one of the other classifier, or one of the vectors for one of the other classes which has much more data. And if it's imbalanced, I mean, haven't worked it out, but I would guess that the angles don't look exactly equiangular, but in proportion to the amounts of data that you have for each class.
Okay. So there is some kind of threshold when you will be collapsing on another vector instead of...
Yeah, yeah, I think that's fair to say. Yeah, yeah. If the class imbalance is not that much, then it's not going to the classifier vectors are not going to collapse onto one another. But yeah, if you have say 1,000 to 1 ratio of samples between the minority class and the majority class, then it is going to collapse onto that. All right, so from this nice, you're able to show that neural collapse happens. So I think you can expect that it should, if you have a large enough deep net that can exactly fit your data set, this is the solution that you should expect. And another thing that we can get from the proof is that weight decay prevents the interpolation and helps orient STD along this. So if you didn't have weight decay, then these would go down to 0, and then you couldn't say anything about the trajectory. I think even without weight decay, you might. I'm not ruling out that neural collapse will not happen, but with weight decay, you're guaranteeing that the trajectory that STD takes is along this solution. And so yeah.
Just a small comment, please. I think weight decay may not be necessary if you use cross-entropy loss instead of square loss.
Oh, yeah, that's right. In the this was all using the square loss. So if you have cross entropy instead of the square loss, then so these terms that multiply your the classifier vectors and the weights, these don't go to 0. So you can still get neural collapse in that case. And yeah, we also run some experiments to show that without weight decay, you don't get neural collapse. With weight decay, you do. So yeah, the story so far, neural collapse is observed as at the last layer, and you can characterize what the solution to training a deep networks looks like at the last layer. And under the conditions of perfect STD, so you never actually exactly converge during STD. So this theorem is not meant to say this is guaranteed to happen all the time, but I think it's more useful as this is the limiting object to which, if you use STD with weight decay, this is what your deep network is going to go towards. So weight decay regularization is necessary. And once we, like I asked earlier, if we know this is what happens at the last layer, what should, naturally you would ask what happens below that. And we explored that in a follow-up paper with Tomer and Marius last year. And so basically, question was, can you use, how far back does this go? And so for this, again, we're going to use the same WL-L-1 to denote the weights of each layer, and then you have the feature vectors. And if we're going to compute the same first order and second order statistics of H for all of the layers. And if you track, we did this for a couple of different types of networks and data sets, MLPs, convnets, resnets on some of your image classification data sets. And let's see what we get. So if you plot the within class covariance and the between class covariance, you'll see that as you go through the network, there's a point at which your between class covariance starts dominating the within class covariance. And from there on out, the rest of the network just pushes this down. So this is the bottom plot is relative values, and this is the absolute value. So since the within class and the between class covariance contribute to the total covariance, it's more useful to see which has a bigger contribution, and that's why we normalize this. So you see that if you track the statistics through the network, you have the within class covariance dominating in the first few layers, and then towards the end, the between class covariance is dominating. Then you can also measure the accuracy of the nearest class center decision rule at each layer, and you see that once again, practically, so beyond wherever your within class covariance is drops below the between class covariance, you can essentially just cut off the deep network from there, and you can get the same performance. Same performance using those features. So in one sense, the rest of the, you've already solved the classification problem somewhere in the middle of the deep network. let's look at the class means and the angles at each layer, and beyond the layer wherever you're within class and between class covariance, switch their contributions. The means and the angles are also going down, and they're approaching a simplex CTF. And finally, if you want to track the feature weight duality, you can't do it anymore using by just measuring the distance for Frobenius norm. So instead, we look at the angles between the subspaces. So you collect the feature vectors, the mean feature vectors into a matrix, and you measure the angle of the subspace in which those means lie with the subspace with the input subspace of the weight matrix. So you look at the correlation between VW and for feature weight duality, and once again you see that beyond the point where your within class and between class covariance switch their contributions, your features and weights are much more aligned. So now this is at initialization, and this is at the end of training. And yeah, so you can see that the neural collapse description really does go down further. So if you have a deep enough, this basically happens when you have a really deep network for a problem that's easier than the deep network that you needed to solve it. So and we also track the rank of the weights. The weight matrices are in fact low rank beyond these. So we plot the top singular values, and you'll see that they all concentrate around 0.1, and the matrices are low rank. The rank is in fact exactly C minus 1, which is the number of classes minus 1, because the C class vectors also lie on a simplex, so they're on a C minus 1 dimensional space. And all of the top singular values are nearly the same, which means that the weights are nearly orthogonal. They're basically all of the, if you do the SVD of the weight matrix, the top singular values are all the same. So that's the rank of the weights. And if you look at the, this is just collecting all of the observations that I was talking about. So we can identify a layer where your between class and covariance dominates the within class covariance, and they form a simplex CTF. They're low rank. Weights are aligned with features, and if you look at if you track the stable rank of the features, you'll see. So we take the feature matrix on the entire data set, and if you compute the stable rank of that, then you see how the deep network solves the problem is first you project your data into a high dimensional space, and then in a high enough dimensional space that you can solve the problem, and then from there on you're basically just reducing the within class covariance and increasing the between class covariance. So the features are also in a sort of low dimensional space, and this was a cartoon I tried to draw to illustrate what's going on. Yeah.
If we cut the network in one of those last layers, do we achieve the same performances?
Yeah. So that you can see in the NC4 slide. So you have exactly the same performance, and I will hopefully get to another demonstration to convince you of that fact. So this is just the same results on a couple of different networks. In fact, so one interesting thing to note is that so for the ResNet you have these kinks along the way, and the peaks of those kinks are at the edge of a residual. So within a residual layer, sometimes you skip one layer in between. So they're more aligned at the edge of the residual connection and less aligned at in the intermediate one. So these are results. In case you didn't believe me before, hopefully there's some more data about this. And one more demonstration that we did was if you replace so you don't train the last few layers of your MLP. We only did this on MLP, so we trained an MNIST MLP by fixing. So this is the number of layers trained. So here we train all of the layers, and here we replace the last the last layer by a simplex ETF, and over here the last 2 layers, last 3 layers, and so on. And so about until the point where the switch happens, you can basically have a network that where you don't train the last few layers to get and basically get the same performance using your network. Okay. Yeah.
You seem to say that for classification, it's like the first few layers that does the work, and then the later ones don't.
Oh, well, it depends on what you mean by doing the work. So the thing that's actually doing the classification is one layer in the, wherever this green line is, I guess the layer just before that, that's doing the actual classification part. But where you're learning representations is in the layers below that.
Do you think the number of layers you need depend on something in the task?
Yeah, so this is CFAR10. I think we all have a general intuition that CFAR10 is harder than MNIST, and MNIST, the collapse happens much earlier than in CFAR, it happens later. So you could think of this as some sort of like measure of the difficulty of your data set. Oh, yeah.
I mean, related to that, do you think there's a notion of instance level difficulty, or there's some, like easy versions of the problem where you wind up directly aligned with the eventual center in an early layer, and then hard instances of the problem like takes you a while to...
Yeah, that's an interesting question. So these are measures on the entire training data set. So this doesn't track instance level. So maybe it might be interesting to track whether whether there are lots of classifiers going along through the network, and easier instances get classified earlier, and later, harder instances get classified later. That would be interesting to try. I don't know, and that's something we haven't thought about. Yeah. So yeah, that was about intermediate neural collapse. And one connection I wanted to make was with associative memory. So you can construct, so these are holographic associative memories. These go back to like the 60s, where people were trying to essentially construct a system that where you can store some objects, or you can store stimulus response pairs, and that returns every time you present the new stimulus, you can get the example that was stored relative to that, sort of like a key value memory storage. And the stimuli were usually noise-like, meaning almost orthogonal, and you can show that this is you can show that you can get a good associative memory out of this. And under neural collapse, you can also show that this is actually exactly an associative memory. So in this sense, the classifiers, or probably any model that you learn with gradient descent, you can think of it as a series of associative memories. If you do a simple computation about the features and the weights, the associative memory solution is exactly the solution that you get from NC3. Okay, so open problems. I showed you a proof for the top layer. How do you do it for the? Can you show how intermediate neural collapse happens? Haven't shown that yet. And again, the proof that we showed for neural collapse was for perfect convergence. It would be nice to get a relationship between the number of iterations that you run STD for and the level of collapse that happens. And So we showed you that, so through this you know that sometimes a deep network can solve an easy problem much earlier. So which layers representation should you use for transfer learning tests? If you use representations from where it's already collapsed, the only information there is about the class label. So is that really useful for another test? You need to think about that. We mentioned dataset difficulty, and now thanks to Jacob, you can think about instance difficulty as well. And how does a deep network do feature learning? What's going on in the first few layers? Can you actually get, maybe neural collapse isn't exactly related to that, but if you know that this is the solution that the classifier learns, can you go back one more layer to figure out what happens there? All right. I'll get to, are there any questions? I'm going to switch gears a little bit to generalization. Yeah.
Do you think that what happens in neural collapse is related to the composition and sparse structure of possibly the function that you're trying to learn?
No, not exactly, because this is, neural collapse just characterizes what happens at the classifier parts, and hopefully you've already built up a good enough representation before that. Now, with compositional sparsity, I think what at least Tommy and others are trying to ask is, are you building a sparse representation before you solve the classification problem? And neural collapse talks about how you solve the classification problem. And I think you can solve classification problems with random features as well. So I don't think it has a direct implication, but you need to, I think it'll be interesting to look at that. This is some new work that we've been thinking about how to connect neural collapse to generalization. But before I talk about this work exactly, I'll give just a couple of slides intro on what generalization bounds are. So remember, in machine learning, our goal is to solve this problem. So we want to solve we want to minimize the loss over a distribution, but we don't have access to the distribution. We only have access to a finite number of samples. So instead, our strategy, since we can't access this problem, we solve either empirical risk minimization or structural risk minimization, where you have some type of regularizer, and you're hoping that solving one of these problems will get you a good solution to this problem. And generalization bounds are all about trying to bound this gap in the worst case scenario, in average cases, however you want to think about that. So the aim is to give a type of performance guarantee, and usually all of the bounds look something like this. So the gap between your true risk, or the loss in expectation, and the empirical risk, or the loss on the particular data set, is at most something that a factor that depends on the size of the hypothesis class that you started with over the number of samples that you have. Okay, sorry, there's a little bit change in notation here. M, going forward now, M is the number of samples. So, why is this useful? You can, since you're actually training a model on the empirical data set, you know what the loss is here. So the aim is to sort of guarantee that your true loss can't be larger than the empirical loss plus this factor. And what this also tells you is that as you collect more and more data, you should expect this gap to go down to 0. Also, that this gap goes down to 0 at a particular rate. So hopefully, using this formula, you can say something like, if I want to improve if I want to improve the loss by 10%, I need to go out and collect 100 more samples. So that's the idea behind trying to give a generalization bounds like this. In the era of deep learning and over-parameterized models, you also hope for somewhat more of a qualitative description, because just because these bounds now are so loose. You never actually nobody actually computes this, right? If you want to find out what the test performance is, you have a test set and you go and measure your test performance on that. You don't actually compute this bound. But so another qualitative use of what generalization bound is useful for is the quantities that determine this bound over here. If I control those, then I will get a solution that generalizes better. That's an intuition. Yeah.
H is only dependent on your model?
Yeah, H is the hypothesis class. That's the model class.
So the second point that if the risk going to 0 and goes to infinity, if the H is only dependent on the model, not on the data, why isn't it automatic?
Yeah, this will go down to infinity. But I mean, so in the these are guarantees from the era of when you had kernel methods and you had smaller models. But how this might still apply now is that what do you do in practice? When you get a data set, you go out and try to build as large a model as you can, right? So you're growing this H along with the number of samples that you get. If somebody comes and gives you more data, you're going to try to train a larger model. So then you can also track how this the ratio between these quantities, how that determines the generalization gap. So so generalization bounds, this is the sort of like a short description of why you might want to do that. And in the era of deep learning, it's less about whether this thing is actually predicting the generalization error, but more about what are this hopefully will give you some information about what quantities to control when you want to find a good solution. Okay, so how do you measure this size of your hypothesis class? So if I have only n functions in my class, then the size is n, right? That was pretty easy. But if I am looking at something that's more practical, like the number of the size of a function class, like all linear functions with a certain norm bound, then how do I measure the size of this class? And for this, we use a tool called Rademacher complexity. If you've already seen what it is, hopefully this will make more sense to you. But if you haven't, I'm going to try to give you a little bit of intuition. So there is a quantity called the Gaussian width of a set, which is basically you have an abstract set. You take the length of the projection of a random vector onto, so the maximum length of projecting your random vector onto any vector in the set, and you take the average over all random directions. And this will help, this is a good, decent measure of the size of your set. Okay? And the Rademacher complexity or the Rademacher width just replaces these, so these are Gaussian vectors. Instead of Gaussian vectors, you just have vectors that are +1, -1, okay? And it's +1, -1 with equal probability. So how do you measure the size of a hypothesis class using Rademacher complexity? So you have your sample, and you map each function in your sample to a vector in Rm, and measure the size of the set in Rm. And that's how you end up with this entire expression here. If I had started with this, it might have been harder, but hopefully you get an intuition for why Rademacher complexity is actually measuring something to do with the size. And there's a standard result that shows you how you can bound your generalization gap with the generalization error with Rademacher complexity. So this is the tool that we're going to use. We're going to try to measure the generalization gap using Rademacher complexity. Let's do a quick example. So if I have the set of all linear predictors with a certain norm, and I have a sample with where all of the vectors are bounded, then I can find the Rademacher complexity fairly easily. I can do it in a couple of lines. So first, start off with the expression, and then just make this into a huge, into an inner product between W and the sum of all the vectors multiplied with their signs. And now you should, hopefully you know how to bound this using Cauchy-Schwarz, and you can pull the norm factor out of here, and then you have the expected norm of this. So this is still a random quantity because you have your Rademacher variables here. And then I'm going to skip a couple of steps. I won't show you exactly how this maps out, but just because these Rademacher variables are all independent, when you compute the square over here, all of the cross terms go away to 0, because in expectation they're all 0, and you're left with only the I terms, and epsilon I squared is always 1, because the variables are either +1 or -1, so you get this. And finally, the bound that you get is b times r over square root m. So in a sense, the size of this, of the set of linear functions with a certain norm depends on just the norm and has nothing to do with the dimension. So that's why, this is one intuition for why the number of parameters that you actually have, that might not actually be a good measure of how complicated your model class is. What matters is more what is the size of that vector. So you can still generalize with high dimensional vectors with low norm. Okay, so that was linear function. That was pretty easy, right? Now, for deep networks, there was a nice paper in 2018 by Golovich, Ratlin, and Shamir. They computed the Rademacher complexity of deep networks, and the basic strategy is you try to peel one layer at a time, and their ingenuity comes in controlling this peeling process so that you don't have an exponential blow up. Instead, you just have something that depends polynomially on the number of layers, on the depth. So you essentially get, so remember in the previous slide we had b times r over square root m. You can see that looks like, here something switched over here. B here is the size of the data. That I should have changed that notation, but so another factor that looks like norm times size of the data over square root m. Okay. Now, all right. So that was a quick intro to generalization. What are the what is the point of trying to? One of the hopeful, useful insights that we get from neural collapse, I think, should be that it describes the inductive biases of deep learning pretty succinctly, and from each of the neural collapse conditions, I think you can get a couple of different concepts. So from NC1, the between class covariance dominates the within class covariance, and this usually means that the features are low rank, and and from there you can infer that the weights also should be low rank. From NC2, the class median form a simplex ETF. The features in the collapse layers are nearly orthogonal. So this is an inductive bias for the weights of the deep network. NC3, the layer weights align with features, and this means that the weights in adjacent layers are aligned. Now, in whatever I'm going to show you in the next few slides, I'm going to focus basically on the low rank part of this to incorporate these inductive to incorporate the low rank bias into a generalization bound, and it's trying to show that we can, if you have low rank networks, then you can generalize better. So the first pass over this, why don't we just throw in low rank and full rank functions into whatever Golovich et al. Did earlier. So the problem here is that if you consider the rank of the class of matrices which are norm bounded and then which have the same norm bound but are supposed to be low rank, you cannot show a separation between these because essentially the insight is that you can do the even with rank 1, you can get the same bound that you get from a full rank matrix. You just set the input subspace, so you just set this rank 1 matrix to be equal to epsilon sum over epsilon I xi, and then a normalized version of that vector, and then you can hit the upper bound. So the key problem here is that you're in the peeling step. You're trying to be, well, to be fair, they're trying to get an effect that depends on the norm. So they're trying to be insensitive to how many components that has, and they measure that through the norm. So you're not going to capture the effect of rank through that. So instead, how can we show a separation between low rank and full rank functions? So if we consider the function classes, so full rank, but with a budget on the spectral norm, and low rank, but with the same budget. Now we can show that the Rademacher complexity of the class depends on the rank. Okay, and the complexity of low rank functions is smaller than that of full rank functions by a factor of square root of the ratio of their norms. And the changes that we made here are spectral norm versus Frobenius norm. So this Frobenius norm controls the overall budget across all the components, not the, instead we use the spectral norm which controls the budget for each component. And don't compute the norm for complexity. Instead, this definition of Rademacher complexity introduces a new variable for each output coordinate of the function. So you have a vector valued function, you have k outputs, and you introduce a new Rademacher variable for each. And you can show the separation between low rank and full rank functions there. Okay, and can we iterate this for deep networks? We can use a chain rule for complexity, which is pretty neat. It allows you to basically, if I have a composition of two function classes, I can do the complexity of the composition. I can split that into the complexity, the Gaussian complexity of, again, this is a little confusing because I'm switching to Gaussian complexity now, but they're the same thing, Rademacher versus Gaussian. The Gaussian complexity of the first function class, and then something that depends on just the second function class. So effectively, you're decoupling these two layers, and this allows us to go one by one down the deep network. So you get I'll try to explain the quantities here. This is the overall Lipschitz constant of the function class f, which is spectral norm bound. The diameter of h, which is the maximum distance between two functions in the function class below, and the Gaussian complexity of Lipschitz coefficients, which instead of measuring the Rademacher complexity or the Gaussian complexity of just one function, you take difference between two functions, and that's what you do here. So if you iterate that, basically you get for the class of deep networks, you get for this particular class of deep networks, you get you can bound the Gaussian complexity as something that's bound on the product of the spectral norms, and then R and H are, so R is the rank, maximum rank of each weight matrix, and H is the maximum width of each weight matrix, and R is the bound on the data again. So you can get a bound that this bound is the Gaussian complexity for deep networks which are rank bounded. So what makes this result not yet clean is the fact that you have this constant to the L here. So this is this is a real problem because this means that the actual complexity looks like it's exponential in the depth, and that's really bad because you don't want things to scale exponentially with the depth. But if you squint really hard and ignore that point, I'll try to give you an argument for why I don't think this factor is real. Okay, so how do we compare to existing bounds? So if you restrict yourself to the class of low rank deep networks, we do a lot better than the existing bounds. So our bound here, if you just drop the C1 to the L, you have the depth times the rank times square root the width. Here, Golovich et al., if you compute it on the same class of functions, you have square root depth times, now the rank is growing exponentially with the number of layers, because they have a product of Frobenius norms, and they all multiply with each other, and now you get something that's growing exponentially in the depth. Then you have, if you look at another bound from Bartlett et al., this is the spectrally normalized margin bounds. They have, their bounds are a little better in the factor of rank, square root r, and then, but a little worse in the factor of depth, L, so square root L. And that's the same for another one. One of these, this is, I think, through a packed Bayesian approach using, trying to bound the flatness or sharpness, and they get essentially similar bounds. All right, so I'll wrap up here. So what was the message I want you guys to take away is that you can show a separation between low rank functions and full rank functions, but in order to show that, you need to look at the right function class, and this can be a little bit of a subtle point. And you might ask me what this means in practice, and right now I think it doesn't mean too much, because in practice you don't have exactly low rank matrices, so whatever, the Frobenius norm already captures whatever savings you have from low rank, so the other bounds are probably better than in this regard. And the other caveat is that our bounds depend on the width, and I think this might not be avoidable if you for this particular class of functions. So these are sort of strikes against this result. And open problems here are get rid of this C1 to the L factor here. So I'll give you the argument for why I don't think that's why I'm optimistic about that. It's because again, in 2015, when people first tried to get norm-based generalization bounds, the first results also had exponential depth dependence on the depth, and then later Golovich et al. Found a smarter way to handle that, so you get a better, you can remove the exponential dependence on depth. So we're working on it, but we need to remove that factor. And another question is, like I said, low rank versus norm. I don't think that's one of the most important questions, because the norm already will capture whatever benefit you get from low rank. But one interesting question, I think, is the product of the layer Frobenius norms the right inductive bias to be minimizing for deep networks? Does this actually capture anything about generalization? And I think if you actually plug in the values into these bounds, the product of Frobenius norms is still quite large, of the order of 10 to the 6 or 10 to the 8 or something like that. So the bounds are still quite loose. So maybe this is still not the right inductive bias. And can we identify either the orthogonality of the weights or the alignment between layers? Can we use that to get better generalization bounds for deep networks? That's another open question. So I'd like to end by thanking all of the people who helped me with a bunch of these projects, and thanks for your attention. Happy to.